Okay, one more time. So chemical symbol represents an element, a chemical formula represents a compound, but a chemical equation represents a reaction. This is a reaction you'll be doing next time we get in lab. We're going to be getting lab. This next time we do a lab, you're in a lab for like 4 days in a row, and then you actually do a write-up, but then you have a lab test. You get credit for the lab write-up, and then you have a test to see how much you learned on it. But the next lab we do is you'll be going from table to table to table in over a 4-day period of time, and there'll be experiments at every table, and you'll spend some time. You said, if you really like that experiment back there, you might go back there twice and say, I'm going to do that one again. So I think you'll enjoy that too. But we still have to get to that point where we can understand what these are right here. So you actually will be taking some zinc, and what is this right here? So we're going to read this in English. Zinc reacts with
hydrogen chloride.
Are you going to do the retest? Oh,
Oh,
can you put your mask on? Okay. All right, one more time. Ready? Zinc plus. Wow. This is supposed to be this is supposed to be the model of the acids with no oxygen, and everybody's supposed to know this one. Hydrochloric acid yields. What's this? Zinc chloride plus what? Hydrogen gas. Okay. Anyway, one thing, you see this arrow? Everything on the left is called a reactant. Now, what's a reactant? Reactants are chemicals that are going to react with each other, possibly, and they find them on the left side of the arrow. So these are the reactants. And what about the products? Where do you find the products? Well, they're the things that will be produced or formed. And then there are some additional symbols that people like to use. I'll make you use them sometimes. Notice that S after this means it's going to be solid. So you're going to take solid zinc and react it with, and all acids and bases are solutions. AQ is a word that means dissolved in water. Aqueous means dissolved in water. And then look at this right here. You see this right here? It's dissolved in water. And this is a gas. So when you do this experiment, you'll take some solid zinc, you'll add a liquid to it, hydrochloric acid, and then you won't see this. You won't see this. You know why? It's dissolved in water. It was formed, but you won't see it. And then will I see this?
Yes.
It'll look like bubbles. This will look like bubbles. You see that? I will see it, because it'll be bubbles coming through the liquid. That's what the additional signals are. And by the way, the person who typed this up for me, it should be a little a and a little q. I forgot to change that. It's a minor thing. But aqueous means dissolved in water. Now, what about this big arrow? What does the arrow mean in a chemical equation? And I was taught, and I didn't know what it meant, but did anybody teach you that it meant yields? Did they do it in middle school? Say, arrow means yields. And you say, what does that mean? Oh, okay. Yields means it produces, it makes, it forms. Everybody get that? Yeah. Now, the next thing I want to ask you about is the arrow. It's also a time aspect. See the arrow? Yeah. This is before the reaction has occurred. Look on the right side of the arrow. Yeah. That's after the reaction has occurred. You see that? So it's kind of like a time thing. Now, why is it called an equation? Why call it a chemical equation? What's equal? Is there something supposed to be equal?
Yeah.
What? What's supposed to be equal? Now, one thing, I want to show you something. I want to go up here. I'm going to try to draw this reaction. Now, watch. I think I'll let this little thing here be zinc. That's my little cartoon character, okay? Plus HCl. There's HCl. And it says it would yield what? Zinc chloride. But wait. And then it would say plus H2. Well, I have a problem here because this says that you're supposed to make H2. and it says you're supposed to be zinc chloride, and something's wrong here, isn't it? Something's wrong. If you had a building set and I said, take these apart and rearrange them, could I do this?
No.
I couldn't.
Yes.
I only have, I have one of those, I have one of those. I have one of here, but I end up with two. How do I end up with two chlorines when I didn't start with two? And so what happens is, when you were in middle school, they probably taught you some of the ways how to call balancing an equation. When you balance an equation, what you're going to do is you're going to make sure all the formulas are correct, and then you're going to add coefficients to the front. Now, this right here will not work, will it?
Yeah.
You cannot take one of those and end up with two. So what they did is, look down here, this is called a balanced equation, and notice I put a coefficient in front of that. So now, here's what it's going to look like. Zinc plus 2 HCl's. See? Zinc plus 2 HCl's yields zinc chloride plus hydrogen gas. Will it work now?
Yes.
Okay, here's one zinc. Here's one H, here's one H. That's two H's, and two of these. See that? And so, have you been taught this in middle school? Do you remember any teacher teaching you how to put these coefficients in front of here? It's kind of, I'm going to teach it to you anyway, you don't, but that's what it's for. When you balance an equation, it makes everything make sense. Now, I never use the word balance when I write formulas. I know that these have to have a net charge of 0, but please don't use the word balance when you're talking about writing a formula. Balancing is used for equations like that. Okay, now, it says here, you can have, it says here additional notes, you can have only one atom of hydrogen in a compound, for example, HCl. You can only have one. But what about hydrogen gas? What if the element hydrogen by itself, not combined with anybody else, what do you know about hydrogen gas? And also oxygen gas, and nitrogen gas, and chlorine, bromine, iodine, and fluorine? What are they? Why did I write H2? Why didn't I write H?
Yeah. Because it's,
On this planet, that's a diatomic element, isn't it? And I didn't do it. And that's just one of those little tricks you have to remember to do. So what's going to happen is, eventually, I might do this. I might only give you the reactants and say, tell me what's going to happen. Now, you don't know enough yet. You don't know enough yet. You get that? But then eventually, you'll be able to predict that, and you'll have to make sure you write zinc chloride and the diatomic hydrogen like that. Now, there's another thing that's interesting about chemical reactions is that, I don't know how much you know about this, but why would people make things out of gold and wear it on their hands, and they might go swimming and stuff like that? Could you make a ring out of sodium and go swimming?
no. Yes.
No, because over here on the periodic table, there's some metals on the far left side. They're called the alkali metals. They all react violently with water. Matter of fact, they react with oxygen in the air. I'll show you some of that. I have some. I'll show you some, not today. But I'll take it out, and I'll make a cut. Those metals are all soft. They're kind of like hard butter. That's still pretty soft for a metal, isn't it? You'll be able to cut it easily. And as soon as you cut it, it'll be really shiny. And within about 3 or 4 seconds, it'll get dull. And that's because it's so reactive, it'll be pure sodium, and all of a sudden, it'll become sodium oxide on the outside. That's how fast it will react with oxygen. So that's some very reactive metals, isn't it? What about gold? Do you think it's very reactive?
No.
It's not. And can I go and find maybe gold somewhere out there in the ground? Yes. How about silver? Yes. Copper. That means they're not that reactive. They're not super reactive. You will never find sodium or lithium in a mine. It'll never be a sodium mine. Remember that movie, that video, Sir Humphrey Davy? He had a big battery, and he moistened this stuff, and he found out that potash or soda ash actually had a metal in there, a shiny metal. And it was so tightly bound that you had to use electricity to unbind it, And that's how he got credit for discovering 3 or 4 elements, that they were all alkali metals. Because you'll never find alkali metals out there by themselves. They'll always be reacting with something, usually oxygen. Could be like chlorine also. It could be something like that. So what I'm going to ask you here is, why do they actually occur? What are some of they're called driving forces? What are some of the things that cause a reaction to take place? Well, here's one. Now, I'm not going to get into the thermodynamics and that kind of stuff, but you can start with things that are 2 reactants, and if a gas is going to be produced, sometimes that is a driving force that makes the reaction take place. Like this one right here, this was the production of a gas, wasn't it? All right, here's another one. Sometimes you'll have, I don't know if you don't know this yet, but acids and bases, whenever they react with each other, they always form water. And the driving force is the production of this really stable thing called water. There could be an energy change. And an energy change could be, have you ever thought about like dynamite? Yeah. Okay, now here's dynamite. And why did dynamite want to do that thing? And what happens is dynamite's this chemical that has high energy bonds. It's really high energy. It's very unstable. And what it really wants to do, and I didn't do it, God said that many things try to seek the lowest, most stable energy level they can get. So you have a high energy compound, and you spark it, and it goes boom, 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 and it changes to a gas. And it wants to change to like nitrogen gas. Nitrogen gas is a tiny little guy, but he's really stable. So here's this nitrogen compound with lots of high energy bonds, and you spark it, and all of a sudden, boom, and it turns into nitrogen gas. Now, think about this. If you had this much TNT, and it changed, all of them change into a million, zillion nitrogen molecules, it would take up about 100,000 times the space that it used to, maybe a million. So what if you had something like this, and in about a thousandth of a second, boom, and it became a million times more volume? What that would do is it would set up a shock wave. It would push all the air very quickly outwards. Boom, 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 boom. Now, that's how buildings get blown down. That's how people die. Now, people die when they're close to an explosion because of that shock wave. For example, in physics, do you know about inertia? Okay, so inertia, an object in motion has a tendency to stay in motion, but what about an object at rest? It has a tendency to stay at rest. Now, so here comes this shock wave, this very powerful wall of air coming at you. All right, it hits the front of your body. It starts moving the front of your body. What's the rest of my body want to do? It wants to stay still. So, and it actually, that's how it kills you. You know, when people jump out of buildings, they do not die because they jumped out of a building. It's when they hit the cement. And what happens is the front part of the body gets stopped, but what's the rest of the part of the body do?
Keep going.
Right. And so that's how that's how you can actually be killed in an explosion that is over there. The explosion could be way over there. And you can still die from that.
What if like a car runs over your back or something?
Say it again?
If you get run over by a car, how does that work?
Even though that's not a chemical reaction, I'm not going to talk about people shooting you or putting a knife in it. So we're going to talk about chemistry mainly here, but it has inertia. Okay, now, so energy changes can make chemical reactions take place, and well, here's another one. I'll do one more. And we'll talk about this in actually a different chapter, but you can start with 2 liquids that have chemicals dissolved in them and put them together, and all of a sudden you'll see a solid. It's like, what? I started with 2 liquids. Why am I getting a solid here? And that was a driving force for that one. All right, so now what I'm going to do is, let's go to the next page. And just like we did when we were naming compounds, humans like to put things into groups, and they try to classify them. We did type 1 and type 2 and type 3, and you know, that helped. By putting them into categories and figuring out what all type 1s have in common, that made it a lot easier to understand. And the same thing here, chemical reactions, they don't all fall into one of these 5, but a lot of them fall into one of these 5 categories. Let's take a look at number 1. This was called a synthesis reaction, and some chemistry books call them combination, but synthesis is the most common word that they use. And do you remember in biology class? You had photosynthesis. It means to take things and put them together, to bind them together into something more complex. Now, if you use light to do that, it'd be photosynthesis. I'm trying to think what else you might have had. Did you ever use the word synthesis? How about, how about protein synthesis? You had that. So here's amino acid, another amino acid, and a reaction takes place to make now 2 of them are joined together, 3 of them are joined together, 4 of them are joined together. That's protein synthesis, taking something simple and making it more complex. So look at the synthesis reaction. A plus B yields AB. Is that pretty simple? So most of the time it looks something like this. A plus B yields AB. This is called synthesis reaction. Now, what I'd like you to do is go down here, and I know you're just starting. Today you're very fresh, you're just starting. Can you find something down there that kind of looks like A plus B, AB? Which one? Raise your hand and tell me which one you think might. All right, Tim.
Number 6 kind of looks.
Okay, I agree. Look at number 6. I think that would be classified as a synthesis reaction. Anybody else? How about somebody else? Wait a minute, hang on, Tim. Just raise your hand if you see another one. Yes, Freddie.
Number 3.
Okay, I'm going to agree with that. A plus B yields AB. So I'll put synthesis on that one. Any others? And I would say, okay, that's about it for the synthesis. Now, look at the next one. The next one, I probably will, when you guys are doing your test or your quiz, I'll let you use abbreviations like synthesis, DEC for B decomposition, or single replacement, double replacement. You can use abbreviations, but take a look at decomposition. That's the opposite. That's the opposite of building something. And now you're taking something and breaking it up. You're decomposing it. So now, here's a compound, for example, AB, and something happens and it splits into A and B. All right, let's see if you find one of those. See if you can find a decomposition. Somebody hadn't answered one yet. Anybody hadn't answered one yet? How about in the front row? Somebody in the front row. See if there's a decomposition. And I'll give you a clue. Most of the time in the decomposition, you only have one reactant. Remember where the reactants are? Anybody?
Where?
Find. Are there any decomposition ones on here?
No.
Okay. So in this case, there's no on this page. There are none, right? Let's go to the next page. Let's flip it over here. Are there any decompositions over here?
Number 2.
Okay. Yes. What do you think, Zoe? All right, number 9. Yes. Okay, look at number 9. That's decomposition. Anybody else? Yeah, go ahead. Any other decompositions?
Yes.
Which one?
Number 2.
Yeah, I agree. Are there any synthesis on this page?
Yes.
All right, anybody? Synthesis, yes.
It's
4?
4.
Yes, I like that.
Number 1.
Number 1. Okay. Any others? 6? Yeah, I like that's synthesis. Any other synthesis or decomposition? Which one? 7. Yes. Now, as a matter of fact, in this case, instead of breaking down into only 2 things, it broke down into many things, didn't it? But it certainly would fit the category it's being decomposed. And that's a giveaway when you only have one reactant and it's going to break down, that's a pretty a giveaway. That's a decomposition. All right, what do you think? All right, now let's go to the next one. Oops. What's another type of reaction that might occur? Now this one, you have to pay just a little bit more attention, okay? The first two were pretty easy, weren't they? Yeah. Okay. Let's take a look. Now watch now. A plus BC yields AC plus B. Now look what happened here. A kicked out B. How do I know it got kicked out? Look, he's all by himself, isn't he? B used to be combined with C, but he got kicked out. And A took his place, didn't it? Okay, everybody look up here. Now, notice that a single element was replaced. So it's called single replacement. Now, here's a hard question for a Monday morning. Do you think A is more likely, A and B, are they more likely to be metals or non-metals? I want you to think about it before you answer, okay? These are just general, like A and B. In this case, do you think A and B are both metals? One's a metal, one's a non-metal. Reese, I'm calling you very often. What do you think? What's your idea?
What do you think, Reese?
That's what I said. Freddie, that's what I said.
Oh.
Okay, you go ahead. What do you think, Reese? You think, are they both metals? One metal, non-metal? And it's not an easy question, I know. Okay, which one's which? And we just started this chapter, you get that? I'm not expecting you guys to know this right now. Anybody else want to take a guess? Yes.
Metal, non-metal.
And which is which then?
B is the metal,
Okay.
and A is non-metal.
What's your thinking about that? Huh?
What am I thinking about that?
Yeah, what made you think like that?
Well, I don't know.
Oh.
I guess because, yeah.
Okay. We just started this chapter, didn't we? Fiona?
Say like A and B are both like metals and C is a non-metal.
What made you think that?
Because it like switches from
Because what?
it switches from A to B, I guess.
One more time. So,
The C switches from A to B, so it
right.
has to go to
I think you're getting close there. Notice that in a compound, if it's an ionic compound, which one's written first? The metal cation or the non-metal anion?
Metal.
So this is probably a metal, isn't it?
Mm-hmm.
Now, notice the A came over and where is it located? First.
Metal too.
So you got that. That's very good. They both tend to be metals. This is a metal kicking out a metal. Now, look at this right here now. D plus BC yields, whoa, BD. See, C got kicked out. But who would kick that out?
Metal.
Non-metal.
Take a look. Look at D. D's written second, isn't it?
Non-metal.
It must be a non-metal. And this must also be a non-metal. So this would be a metal kicking out a metal. And this is a non-metal kicking out a non-metal. All right, let's do the next one now. Well, let's go down here. See if you can find a single replacement reaction.
Did you say the second one was a non-metal kicking out a metal?
No, non-metal, non-metal.
Come on.
Wait, does anybody see one here? It looks kind of like a single replacement.
Yeah.
All right, Will,
Probably 5. Yeah. So.
take a look. Now, zinc kicks out hydrogen. Now, even though hydrogen is not a metal under our normal circumstances, it is written as a cation, isn't it? And so hydrogen gets kicked out. So I like that one. That is a single replacement. Is there another one?
One.
One? Okay, now one, I'll tell you what's different about one is here's A, B, and here's C, D. So I don't have I have something a little different there.
9.
All right, 9. Okay, now 9, take a look at 9. since that one says single replacement, what do you think would happen over here then? What do you think I should put on this side of the arrow?
ALS4 plus C. Yeah.
Okay, now, great learning opportunity. All right, ready? Everybody ready? I never said that you simply, wherever the CU was, you put an AL. I never said that. I said AL kicks out CU and AL forms a compound with the other thing, right? Now, how does aluminum form a compound with sulfate? You think, so what's the charge on sulfate?
It's -2
What's the charge on aluminum?
+3.
Okay, so you can't just cut and paste the aluminum and put it next to sulfate. You still have to know the rules of writing compounds, don't you?
2, 3.
Now, that should bother some of you because just like when I began the lesson, you said, wait a minute, I only see one aluminum here, and you end up with two. How do you end up with two aluminums when you only start with one? Well, I'm going to fix that by doing what? What's that B word that means you're going to put coefficients in front of things to make it make sense?
Begin.
And unfortunately, when I was your age and somebody said we're going to balance an equation, the only time I'd ever heard that was in sports or in PE class, balance. But I didn't know anything about people who have checking accounts, and you get this thing in the mail, and you actually can check and say, hey, I put $2,000 in the bank, I spent $1,500, and the bank says I have $500 left over. And in my calculations, I have $500 still in the bank. That means it balanced. If you're a bookkeeper, an accountant, if they balance, it means that all the money's accounted for. Hang on just a minute, okay? So here, everything has to be accounted for. Now, can you take a look at this right here? How many sulfates do you have?
3,
How many here?
4,
No, don't do that. How many sulfates?
0.
Don't do that either.
Dude.
Okay,
Whoa.
how many sulfates? How many sulfates?
4.
Okay, try it again. On the left side, how many sulfates? Okay, stop.
On the left,
Yeah, how many?
1,
That's right. How many over here?
3.
Okay, so I'm gonna put a 3 here, right? But how many coppers does that give you? That thing distributes over everything, doesn't it? How many coppers does that give you?
3.
There you go. We're gonna do balancing equations tomorrow. All right, anybody have any questions? All right, good start. Now, if you want to glance at the book, a little bit,